Welcome to General Chemistry Lab. This week we're going to be working on a titration. It's an acid-base titration. And so we're going to actually do two titrations. The first one is a standardization. So we're going to make a sodium hydroxide solution of a approximate concentration, and then we're going to standardize it so that we know the concentration very exactly. And the second part of this then is to titrate an unknown acid, and that unknown acid titration will allow us to determine the molecular weight of the unknown. We have some objectives. We're going to try to learn some new language this week. We're going to learn molarity, primary standard, the standardization, what that experiment is, and then of course titration. So we're going to work on our calculations involving that. So we already know that substances react in whole number ratios, and we can measure the amount of reactants and products via grams, volume. If it's a gas, we can use pressure or volume for that also. And if we know a specific amount of one reactant, and we know how many grams of it is that are pure, and then if we can take a second chemical, let's say it's a solution, and we know its volume very exactly, then from the grams of the pure substance, we can determine the concentration of the second reactant. And so that's what we're going to do. We're going to titrate with a burette to do that. All right, so once we get that done, then, well, you'll have a known concentration or standardized sodium hydroxide solution. All right, determining endpoints. All right, there's a number of different ways we determine endpoints in titrations, and we can use a pH probe, for example, in an acid-base titration to follow the curve. We can do turbidity or changes in the solution, or color, and in fact we're going to use a colored indicator today, or one that goes from clear to a purple color. And so that indicator will allow us to see the end point of the reaction. I've got a pH graph on this slide, and this is actually showing a strong acid, a pH 2, and it shows the pH changing as volume changes. And we get to a point where the curve becomes very, very steep, right? And then plateaus again. And at pH 12, we're using a strong acid to titrate with. But the end point for the titration is in the middle of this, right? So right about where this point is. But if you'll notice, because the pH changes very rapidly, those points become very scattered. Now, we'll later on learn a mathematical technique to find the middle of that, or a couple of them, and especially if you take my quantitative chemical analysis course. But and we'll use pH probes to do some titrations later on in next semester. All right, don't forget stoichiometry. We're going to solve for moles again, right? And so we're going to use the titration as the physical part of the lab to set up calculations in stoichiometry. And so remember our three steps. We're going from something that's known, whether it be concentration or mass, to moles, and moles of A to moles of B, and then moles of B to our final answer. And so we're going to actually end up in a different place with this lab than we've been doing in class. But so the beginning of this, the first part again, is the standardization of the sodium hydroxide. And because bases, especially like sodium hydroxide, it reacts with CO2, carbonic acid forms in the water and can change the concentration. And so it's hard to make it accurately. So what we do is we make the solution close to a value that we want, and then we find a primary standard, okay? And the primary standard is a chemical that can be obtained very pure. And so today's lab, we're using potassium hydrogen phthalate, which is a primary standard. Now, that compound is easily weighed. It's very, very pure. It dissolves easily, so we don't leave behind crystals and change the chemical reagent. And that compound is what we consider to be a primary standard, okay? KHP is the abbreviation that we use for it. Be careful because this is not potassium hydrogen phosphate, right, or phosphide. This is potassium hydrogen phthalate. That is an abbreviation. And so it's actually has a molecular weight of 204.23 grams per mole. So anyway, the reaction we're using for standardization is that sodium hydroxide, and here's actually the formula for KHP, potassium hydrogen phthalate, and as you can see it's a little more complex, but if you'll notice that the hydroxide comes along and removes a proton from the KHP, an acidic proton, and it's a 1-to-1 mole ratio. That's an important concept because we're going to do mole conversions. And so once we have it standardized, then we're going to use it to determine the unknown moles of acid. You're going to weigh an acid that we're going to give you. We're going to call it unknown. And you're going to be able to titrate with your standardized sodium hydroxide solution to find the number of moles of the unknown acid. And when you do that, then you're going to have the mass of the acid and the moles of the acid, which will allow you to combine those to make a molecular weight for the unknown acid. And so that's the second part of the experiment. Now, just to practice those calculations just a little bit, I have one on the board, and this is your standardization calculation and an example of that. And so if I start with 0.6799 grams of potassium hydrogen phthalate, and it's titrated with 19.24 milliliters of sodium hydroxide, find the molarity of the NaOH. And so we put the weight of the KHP up, and we multiply that times 1 mole over 204.23 grams. And this is for the KHP. So now we've converted the grams of KHP into moles of KHP. And for every 1 mole sodium hydroxide, there's 1 mole KHP. And so now we've done a second conversion to moles of sodium hydroxide. And to find the concentration, then what we would do is divide all of this by the volume in liters. That would be moles per liter, molarity. And so the volume is 24 liters NaOH. So now we have terms moles per liter in the calculation. And when that's answered, in this case, the concentration is 0.1730 molar or moles per liter of sodium hydroxide. And so this is an example. You'll have to do this calculation as one of the calculations to complete your lab. And so this calculation is following what we've done earlier, where we started with grams of KHP and we went to moles of KHP using the molecular weight, and then we used a mole ratio from the balanced equation to go from moles of A to moles of B, and then we divided the moles of B by the volume of B to get the concentration of it. And so that's the concentration of the sodium hydroxide to follow it on our mole roadmap. All right, procedure-wise, all right, a couple of things that are important. I'm just going to pull all these up. And so to standardize with KHP, there's a couple things. The lab handout starts with talking about a weighing flask. Now these are breakable, they are glass, so be cautious with them. But these will be dried in the oven to have the KHP be very dry, and then be cooled in a desiccator and then capped when they're put by the balances. And so the KHP then, what you're going to do is take the vial itself and put it on the balance and tear it, and then you're going to take the lid off, and leaving it on the balance, you're going to remove about 3 to 4 scoops from a small scoop, to get the mass that you need. Be paying attention, watching the balance. It will tell you how much you've taken out. And once you've removed what you need into your Erlenmeyer flask, right, then you would recap the vial and take the final weight so that you know how much you've put into your flask. Then you would take water once you put it into the flask, and you would dilute it with, I think the lab says, about 20 milliliters. Now, the volume of water here is not as important as knowing the mass of the KHP, because that's what we're using in our balanced reaction. And so once you have that in there, now there's one other thing that you can't forget to add, and that's the indicator. You need a color indicator put into here, and that indicator will change color when we reach approximately that midway point on a pH graph. Now, there's other things I want to talk about with titration. Number one, when you get done, always store your burette tip up. When you get ready to use it, turn it over, and you're going to rinse it first with your sodium hydroxide solution, okay? And you're going to then drain the tip and make sure that there's no air in the tip so that your first delivery is an accurate volume delivery. Now, technique-wise, when I'm titrating, normally I titrate where I can see my flask, right? And I'm swirling it, and so I'm watching the solution drop into the flask as I'm swirling, and I'm watching for a sustained color change that holds for 30 seconds. As I approach the end point, that red will stay longer and longer, and so you'll need to slow down the volume delivery as that approaches. And so in that technique. Oh, one other thing I kind of forgot to mention, when I'm filling a burette, don't forget, guys, never fill one above your eyes. Put the burette below your eyes, and when you use a funnel, take your thumb and lift the funnel so that air can go in, and then fill slowly up to the point that you need it to be filled. So I'm going to put this back in the stand, tip up to store it until lab time. All right. So part 2, you're going to repeat that same procedure, except you're going to do it instead of with KHP, you're going to do that same procedure with your unknown acid. So you're going to weigh your unknown acid, place it in a volumetric flask, dilute to volume. Actually, you don't even have to, if you weigh it and have a known weight, then you should be able to just measure it directly from the mass. And then you're going to add 2 or 3 drops of phenolphthalein. And don't forget to do that. Make sure your tip's clear and titrate till you get pink. And then you're going to use those results to calculate the molecular weight of the unknown acid. Your end point is a very, very light pink, just a touch of pink. This is too dark. Try to get it as light as possible, but with a color change, and that's the volume of the change. I'll teach you some other tricks in lab, such as washing half drops off and those types of things when you get close to the end point. All right. Safety this week, we're going to wear our safety glasses. You're going to wash off any acid or base that splashes on you. They're very low concentration. It's a neutralization reaction, and everything can go down the drain. So I will be excited to see you guys in lab, and have a great week.